Yeah, so thank you for the nice introduction. So yeah, let's dive right in. So let me just start off with a short video of our approach. So what you see here are video snippets of scenes which have been rendered with our approach in real time. And what you see there is diffuse shy, glossy reflections, sharper reflections, and also support for multiple viewer. So basically, this paper, as the title already suggests, is about computing global illumination in real time. And our goals here are having diffuse shy, having reflections, having multiple line bounces everywhere, and also all that with support from multiple viewers so that we can share computations between them. Now, for related work, so the Radiance probes are now commonly integrated into game engines, but they suffer from light leaks or suboptimal probe placement, and they overall have lower lighting quality than with screen space denoising. So here usually the scene is path traced with one sample per pixel. This produces a very noisy image, which is then fed to a denoiser and basically tries to reconstruct the image, but there are cases where it fails if the images are simply too noisy. Then with Unreal Engine's Lumen, so screen space radiance caching got a lot of attention. So what happens there is that radiance probes are placed on the surface in screen space, and basically they capture the incoming radiance, which basically then allows to integrate the ODBF at full resolution. AMD Chai built on top of that. They introduced hash grids as a second level of radiance caches that provide the radiance for the screen probes radiance caches. Our approach falls under the same category as screen space radiance caching, but with the twist that we are not operating in screen space, we're operating in texture space all the way. Yeah, and for that we're using on-surface caches, and this also has some nice benefits we will see later on. So for on-surface caches, basically they were introduced with the goal of sharing computations between multiple viewers. And the idea behind it is that if you have multiple viewers looking at the same objects, triangles will get shaded multiple times, and redundant computations are basically performed then. So the image below is just an example. So you have the bistro interior scene, you have a lot of viewers on the tables, like a VR chat kind of type experience. And in the middle image, you can see the overlap. So red is a lot of overlap, blue less, and white is no overlap at all. And the graph to the right basically shows the sublinear scaling for the computations, which basically decreases with the number of viewers then. Yeah, so sharing computation in screen space is not really possible or really hard. So on-surface caches are a texel shading approach, which basically allows the viewers to be allows computation to be shared between the viewers inherently. And in the paper, they've shown that the quality matches those of screen space renderers, and that the overhead of the cache management is actually minimal. The scene geometry is split into so-called islands, which are a connected group of triangles. And those triangles are grouped together based on their normals. So basically, this ensures that they can represent it in texture space without much distortions. And yeah, the image to the right is just a visualization of such islands where they are color-coded. Yeah, so bistro interior, like the example from before. Yeah, in texture space, you have access to neighboring texels, which are on the same island. So this is very useful for filtering, but there's no access to neighboring islands. And the on-surface caches also provide a convenient mechanism to control basically the resolution of those caches through MIP biases. And those MIP biases work exactly the same as the regular MIP bias you have in textures. So by increasing the MIP bias, the resolution of the caches decreases and vice versa. I will talk about the MIP bias in a couple of slides, but for now it's basically just important to know that it's a tool to control the amount of radiance caches then later on. The paper also had a GI solution which stored the radiance in the surface caches. This is an example how it looked like. At the first glance it looks nice, but when you look closer you can actually see that surface detail is lost because the radiance was computed based on the cache resolution, and there was no way for the BHF to be evaluated in the full resolution. And so the irradiance here is only interpolated between the screen space pixels then. And you can see this if you increase the mid bias, so you lower the resolution, you get this blurred out like walls, and here on the payloads you can see it gets blurred out. Of course, if you have a mid bias of 0, you can still preserve those features, but it's simply, the computational cost is simply too high then, computed for every pixel. And another disadvantage is, so there's no multiple bound support. I mean, you can trace more rays, but this is a bit more expensive. And also no reflections, so only diffuse GI. So basically, we propose a radiance caching scheme with on-surface caches, providing unified radiance caching in texture space. So we cache radiance on the V-buffer hits, so the primary hits as well as secondary hits, and both store the radiance over a hemisphere. So basically, this allows the radiance to be sampled from every direction. This comes with some nice benefits we will see later on. The primary caches store the incoming radiance, so you can integrate with the BRDF at full resolution later on. Secondary caches store the outgoing radiance, so here the BRDF is already evaluated. This will lose some surface detail, but it doesn't really matter since secondary caches are used as a coarser radiance cache and only serve as basically a source of radiance for primary caches most of the time. For secondary caches, we also want them to, so we want to quantize them to span a larger surface area. So we use, for example, around 30 by 30 centimeters. And this allows for easy reuse, because each ray which hits the surface then basically will always interact with the same secondary cache. Let's have a look now at the cache interactions. So how do the caches interact with each other and with the scene? So basically, it all starts with the camera. From the camera, we get the V-buffer, and from the V-buffer pixel, basically, we allocate them all the primary caches. And how many of them basically then are controlled with the mid bias. So for each V-buffer pixel, we try to allocate a primary cache. Then from the primary cache, we start casting secondary rays. Those secondary rays will hit the surface, and if there is no secondary cache, then we allocate one. And if there's one, we can actually then sample the outgoing radiance and use them as the radiance for our primary caches. The secondary caches sample direct illumination. We use resteer for that. Then we compute the outgoing radiance. So we have to apply the BRDF for every hemisphere texel. The hemisphere solution of 8 by 8, so we have to do 64 BRDF evaluations per light sample. Maybe this sounds a little bit much, but actually it's very fast since there are not so many secondary caches. To get multiple light bounces, we simply let the secondary caches sample each other. So remember, we have the radiance of the hemisphere, so it's very straightforward. And so we get multiple bounces over time then. And we simply do this by generating 32 or 64 rays using a cosine distribution. We didn't look at any other distributions because it already worked quite well here. And in case any of the secondary rays from the primary cache hit the environment map or emissive surface, we can actually get some radiance from direct illumination in there. For emissive surfaces, this works quite well as long as they are not too small, because then the chances to get hit get lower and lower, and you may get some flickering artifacts then. So the pipeline looks as follows. So the reddish colors are passes which need to be executed per viewer, while the bluish ones are viewer independent. So it all starts with our visibility buffers. Based on the visibility buffer, we gather all the primary cache allocation requests. Then the next stage, we deduplicate all those requests, both for primary and secondary caches. Then we start updating our secondary caches, followed by primary cache update. The primary cache update cuts the secondary rays, and those secondary rays then would actually gather the secondary cache requests then. And basically, this means that the secondary caches then will be allocated in the next frame, and then, so basically it's one frame later only. And at the end, for each viewer, we render with the caches, apply post-processing, then you have your final output frames. So let's talk a little bit about the mid bias now. So mid bias is used for lowering the cache resolutions. Having Radiance cache for every screen space pixel is simply too expensive. It's too much compute and memory. Therefore, we want to have caches span a larger area. And using the MIP bias, we can control the size, but as you probably might have already seen, there are some artifacts here. Those are those black areas here. And what happens here is that the ray starting positions fall actually inside geometry here. And this is because the triangle ID resolution is not high enough, so there are bad triangles then picked for ray starting positions. So what is the triangle ID? The triangle ID is needed to go from cache or texture space back to world space during the update passes. And the original OSC paper basically used only the same resolution for that, so the triangle ID and the effect resolution had the same resolution. And this causes some issues. So in the images down there, the leftmost is basically the scene with the triangle IDs, and the image to the right, so this square inside basically should represent the cache and the chosen triangle ID, which is 7 in this case. And so what that means is for the entire cache, only ray start positions from triangle ID 7 are chosen, and this is only a subset of the surface from the cache. And if this triangle ID 7 is actually occluded, then you also have this black pixels like before. So to fix that, we separate the resolution of the triangle IDs, and we found that a difference of 1 or 2 MIP levels is already enough to solve those issues. So if you look again, so the image to the left was before, so with the original resolution, and by decoupling it, you get a significantly better ray starting positions there. Now, let's talk a little about the secondary caches a bit more and how we share them, or how good they can be shared. So secondary cache reuse is quite high, even with only a single viewer. The image below is a visualization of the reuse. Black means there's no reuse, and the reddish color, or the red color, basically means 20 or more times was the cache reused in the frame. And this is the secondary caches basically span a large area, causing the secondary rays from the primary caches, hitting them all the time, basically. And this is especially true in corners, like here, or in rooms. Then you get a lot of reuse there. And what's also nice is that when you have multiple viewers, they don't even have to overlap the views. So they only have to look, basically they only have to be in the same vicinity, because all the secondary caches are all around the viewers all the time. So the only thing for them to be shared between multiple viewers is that they have to be in the same vicinity. For filtering texture space is straightforward. So for temporal filtering, you have no reprojection, because the caches are stored on the surface and independent from the view. We use an exponential moving average, and the blend factor is inverse to the sample count. For spatial filtering, again, there is no depth or normal check heuristics necessary, because the texels are guaranteed to be in the same surface. Yeah, there we apply blur with radius of 3. We use a single angle area detection as Wright and Boise. And we also use parallax corrected directions when we fetch radiance from the neighboring texels. And this corrected directions preserve important lighting features. As you can see here in the curtain here, in the wrinkles, you can see that without the correction it looks more flat, while as with corrections you get this nice looking shading in there. Another thing is, with the primary caches we have MIP levels, so basically they vary depending on the position of the camera, and we have to ensure that we have a consistent density of caches in screen space for the primary caches. And as a result of that, new caches or new primary caches are allocated during a MIP level change. And of course, you want to initialize them with proper values, or else you have some popping or flickering artifacts. And to prevent this, we look basically search in adjacent MIP levels for valid cache entries, and we use them then for the initialization of our newly spawned probes. And if a MIP level change occurs, there will be a valid cache entry in the lower and the higher level. And this is how we ensure a seamless MIP level transition. For the radiance evaluation, basically there are two cases. For the diffuse case, we rely on spherical harmonics. They're well known. They work quite well with low frequency lighting. And for cluster reflections, we're also able to important sample our primary radiance cache hemispheres. So we apply BRDF important sampling for that. And for sharper reflections, we can trace dedicated reflection rays, which then hit secondary caches. So for the BRDF important sampling, the result is still noisy probably, or very probably. And since we have to do not cast any rays, we can increase the number of samples to reduce the noise. But there's one thing, we have to try to interpolate between the BRDF important samples to avoid any blockiness. And this means you have to do 8 radiance fetches per sample. And this is actually expensive because those fetches are basically spread out in memory. To fix that or to improve that, we do stochastic Trinity interpolation. So based on the interpolation weights, you pick a sample. And basically what this means, you only have one radiance sample, one radiance fetch per sample. And basically, what this means is it causes a little bit more noise, but easily mitigated by filtering. For tracing dedicated reflection rays basically allows us to achieve sharper reflections, and these reflection rays simply get their radiance from the secondary caches, since they already store the outgoing radiance, and we can sample them from every direction, so we don't have to cast any further rays here. And additionally, our secondary caches also handle multiple bounces. So what that means is that our reflections also capture multiple bounces. Now let's go over to the evaluation. So for performance for a single viewer, we evaluated 4 scenes. In 3 of them we were faster than AMD-GI. In the last one, in Bistro Exterior, we were slower. And what we observed there is that we saw an increased cache allocations of our approach due to the foliage. And since we try to allocate a cache for every pixel, foliage, basically with fine and detailed geometry, we will have more caches and therefore be slower in that case. For memory, we reduced the block size to 2 by 2 instead of 8 by 8 compared to OSC. So what is the block size? The block size is basically how many caches are allocated at once. So basically a chunk of caches to avoid having to allocate for every single cache all the time, basically. And this resulted in a reduction of memory usage up to 14x. And this is because if you have a too large block size, all those caches in there are unused, especially when you deal with fine and detailed geometry. So what this means is for foliage, foliage causes a lot of memory, and this is exactly what we observed here. So for a single viewer, we had memory requirements for both caches around 300 megabytes, up to 700, and those 700 came from Bistro Exterior because due to the foliage and the fine geometry there. Now for multi-view evaluation, we conducted an experiment with increasing number of viewers and fixed overlaps. So the gray dotted line should basically be the screen space reference where each view is rendered separately. And the other lines, the colored lines, basically are render timings for different overlaps. And as you can see, higher overlap and more viewers lead to greater savings and shows the sublinear scaling here. The next experiment was in the 0-day scene. So 0 day is highly dynamic. We had 16 different camera paths in there. And basically what this scene did is stress test our system because all the moving object causes a lot of cache allocations and deallocations. The red line indicates the overlap, which was around 40% in that case. And our method outperforms the screen space reference. And compared to the previous OSC approach, which is the orange line, we are a little bit slower, but we also deliver better quality, have multiple bounces, and can also support reflections there. Now for quality, we compared quality to AMD-GI. Ground truth was generated with the path tracer from AMD-GI's framework for fairness in this case. Our approach achieves better image metric scores across the scenes, and we attribute that to so that we can preserve more detail upon closer inspections, for example, at the Pika scene, due to the placement of our caches. For glossy reflections, so very important sample, the primary radiance cache, the results are very similar. One could argue that we are slightly closer to the path traced reference, but yeah, they are very close. But in the case of having multiple bounces, here you can see an extreme difference. So what you see here is that our approach can basically capture the multiple bounces in the shaft of the scene, whereas AMDGI is unable to do that because they can only handle multiple bounces. They cannot handle multiple bounces outside of screen space. So yeah. So what are the limitations and what future work is? Basically, one issue are island borders. With the extensive filtering in cache space, we observed the appearance of island borders. And these borders occur because cache taxels do not have access to neighboring islands during filtering, even though they maybe would lie in the same surface. And you can see this in the image here, for example, the bottom, the left two. So you can see the golden vase and the island visualization to the right, and you can see exactly those borders in the final rendering too. So this is one limitation right now, and this would be a nice future work to actually maybe get better island generation in that case. Another limitation right now is handling of fine geometry, like foliage. So basically this is the bistro exterior scene where we saw the increased cache allocations. Yeah, since our approach now tries to allocate caches for every rebuffer pixel, having a lot of foliage and fine geometry basically leads to increased cache allocations there. And this would also be nice to do some further future work here, somehow to reduce those allocation-headed cases. So to conclude, we presented a radial caching system which works solely in texture space. We are capable of handling multiple bounces everywhere. We support reflections, and all that is also suited for cloud-native rendering for multiple viewers. And yeah, our quality and speed matches, sometimes exceeds also the state of the art. Thank you very much.
Thank you. We have a few minutes for some questions. In the back, I think.
Can you explain the pros and cons of this service, all service cache versus the mesh cards?
So the question is the difference between this approach and the mesh card of Lumen, right?
Yeah, the pros and cons. We compare this all service cache with the mesh card.
Okay. Yeah, I would say that one advantage here is that we place our caches directly on the surface, so we have no approximations there, basically. We only scale the size of the assets directly on the surface. And I think this also helps to mitigate any light leaks or something like that due to, basically due to cards which are not directly approximate the surface good enough. So I think that's one advantage there.
Is there any disadvantages compared to the card?
Disadvantage, yeah. Basically the same problem we have with primary caches could also happen for the secondary caches, for example. If you think you have foliage there, we now maybe are too specific there, so we place too many caches on the foliage, basically. This would one disadvantage which I also said from future work. So,
Another question?
First of all, this is extremely good work. I'm curious, how are the islands set up? Like, is that a pre-processing step, or is it done at runtime?
So the question is the island generation a pre-processing step or done at runtime? It's a pre-processing step, so we actually generated the islands beforehand and then saved them to some file which we load then on startup, basically. But yeah.
Another question here?
Is the source code?
Sadly, there's no source code because it's a cooperation with company and we are not allowed to publish it right now.
I had a question. Have you tried things like moving lights or moving geometry and how that works?
Yeah, so the zero-day scene had a lot of moving geometry, for example. There is a video of that with our submission. So
Okay.
there is, yeah. But we support it. Yeah.
Cool.
Yeah, when you say cloud-native rendering for multiple viewers, I assume this is using one copy of the caches at all levels.
So,
All the clients that would.
so the question is basically about how the cloud rendering would work with this approach, right? So basically, all the viewers had to be in the same scene or in the same instance, and there would be basically a cloud server with multiple GPUs, and they basically are distributed over the effects. So one effect would do direct lighting, one effect would do ambient occlusion, and one effect would do, for example, this stuff here. And basically, one GPU, for example, would generate all the V buffers, then distribute the V buffers to the different GPUs, and then those different GPUs generate the outputs, and then they're combined and then sent per frame buffer streaming to the client. So this was the proposal from host surface caches, basically.
Okay, I think we're out of time. So let's thank Wolfgang one more time.